Bem, bom dia a todos. Então, acho que vamos começar nosso seminário de hoje, né? Eu sou Adriane Sandoval, gerente de consumíveis da empresa Analítica, que é representante da Avantor no Brasil. Hoje nós estamos trazendo para vocês, em conjunto com a Avantor, esse seminário Teoria e Prática e Transferência de Método por Cromatografia Líquida, né? E eu gostaria de agradecer primeiro a Mrs. Gemma Lô por essa apresentação. Gostaria de agradecer a todos os participantes desse evento, aos cromatografistas, aos pesquisadores, ao pessoal de apoio da Nova Analítica, enfim, a todos que estão atendendo a esse seminário. Então, hoje a gente vai passar aqui aproximadamente 1 hora, né, falando sobre essa técnica, né, sobre os problemas analíticos, transferência de métodos, e vamos falar um pouquinho da Avantor. Quem que é a Avantor, né? No Brasil, esse nome é novo, né, Avantor, mas, na verdade, ele não é tão novo assim. A Avantor, na verdade, ela vem lá dos tempos antigos, né, ela foi fundada, na verdade, em 1904, por John Townsend Baker, né, o fundador da J.T. Baker. Ele tinha um propósito, ele era um químico da Pensilvânia e tinha o propósito de produzir padrões químicos de alta pureza. E assim ele criou a J.T. Baker. A J.T. Baker, com o passar dos anos, ela foi se inovando e com o propósito de expandir a distribuição de padrões de alta pureza para o mundo inteiro, ela foi adquirindo várias empresas, entre elas a VWR, né? E entre elas também, em 2018, a empresa ACE, né? Que é a ACE, que é a fabricante das conhecidas colunas ACE no Brasil. Então, hoje, as colunas ACE, elas são chamadas de Avantor ACE. É assim que elas estão chegando hoje para a gente. Quanto à nossa querida apresentadora, Mrs. Gemma Lô, ela é de formação bioquímica, ela tem mais de 10 anos de experiência trabalhando na Hycron, ACE e agora na Avantor, em desenvolvimento de métodos e no suporte de desenvolvimento de métodos e de troubleshooting, quer dizer, implantação de métodos, resolução de problemas, de HPLC e UHPLC a suporte de clientes, né? Ela também é responsável por todos os seminários e atendimento de clientes, né, da Avantor hoje. E devido à sua formação em bioquímica, ela também é expert em análises de biomoléculas e também de analitos polares. Então, eu tenho certeza que a apresentação de hoje vai poder ajudá-los bastante a escolher uma coluna, desenvolver um método e também detectar um problema analítico. Então, eu espero que vocês fiquem contentes ao final dessa apresentação. Perguntas serão feitas no final da apresentação e também poderão ser mandadas para a nova analítica depois, né, que também a gente estará respondendo, tá bom? Então, eu passo agora a palavra para a nossa querida Gemalu, para iniciar iniciar o seminário. Gemalu, good morning, Gema. It's please go ahead and have a nice seminar. Please, it's your turn.
Thank you so much, Adrian. And let me just load my presentation. There we go. So, good morning, and thank you very much for inviting me to talk about HPLC and UHPLC method translations. We will talk about the reasons why people want to translate their method, how to do it correctly, and perhaps help with some problems that you have with your method transfers. Firstly, thank you very much again to our partners, Nova Analytica. We have worked together for many years and long may it continue. Thank you for your support. So there are many reasons why people might want to translate their method. Normally, it is because they want to increase the speed of the separation, so faster run times. And you can achieve these by moving your method from a large column to a small column and achieve the same performance. So you get the same results, but you spend less time on the analyses. One way to do that is using UHPLC, so high pressure chromatography, but you do need UHPLC instrumentation for that to really speed up the methods very, very quickly. Now, I can show you that you don't need to go to UHPLC systems. You can speed up your method and be more productive on an HPLC instrument if you just use a smaller column with a smaller particle size. You may have the opposite. So you have a method on a UHPLC system and the lab you're transferring the method to doesn't. So you need to transfer the method back to HPLC. Something that's been very popular in the past 10 years is the solid core particles. Now these fused core, solid core, superficially porous particles give lots of advantages for your method. So you could move from a fully porous particle to a solid core particle and speed up your method. This will give you advantages of time, but also you will save solvent and therefore for money in the long term. Perhaps you want to speed up method development. If you have many compounds, the faster you can develop a good method, the better. Perhaps you want more information from your sample. So higher resolution, better separation of those peaks, higher peak capacity in a gradient method. You can achieve that by translating the method to perhaps a longer column or a column with a smaller particle size. And finally, some methods do not work well when you move them to a different instrument. And there's very good reasons for that. So we can look at transferring one method in your lab on one system to another system and making it work, because there are some things to consider. So we're going to start with Isocratic methods. And Isocratic translations are more simple to do, and they should work every time if you follow these instructions. So when I'm talking about an Isocratic method, I mean I have a constant mobile phase for the period where my peaks elute. You may have a gradient at the end after the separation to clean the column, but where the method is isocratic, we're going to look at that section of the chromatogram. So generally, if we want to speed our method up, it's a good idea to choose a column that has the same length to particle size ratio. And this is written here as L over dP. What that means is you have a column with the same efficiency. So you should be able to achieve the same performance from a smaller column with a smaller particle size. For example, at the bottom of this table, you can see different column lengths and different particle sizes. So for a 300, so 30 centimetre column, that has about the same efficiency if it's 10 micron particle size as a 15 centimetre column with 5 micron packing material. So now I've halved the length of my column, but because I've also reduced the particle size, I've got the same potential efficiency from the column. If I want to go even faster, I could go down to a 75 millimeter length column, but now I need a 2.5 micron particle size. You can see in the table these all have similar efficiency of 30,000 plates. So when you decide to speed up your method, consider that length to particle size ratio, because that will give you the same potential efficiency from your column. But halve the column length, halve the runtime. So now I have a more fast separation and more productive in my lab. Now, this slide may look a bit scary, lots of equations, but I will show you a nice calculator we have made to make this very simple for you. And everything makes sense. If we think of our translation, we're going from a large cylinder to a smaller cylinder. So we need to scale our injection volume because now we have less volume in our column, and that is scaled based on the ratio of column volumes times by our original injection volume. And we also need to scale the flow rate. If we change particle size and if we change the column ID, so the actual dimensions of the column. We can use these scaling factors and the results from those experiments to give us a new runtime, so we can see how much time we've saved. And also, it can be used to work out back pressure. And this is very important if you are pressure limited on your instrument. For example, if your system goes to 400 bar, you can use the calculation to check your new method stays below the 400 bar limit. The smaller the particle size you use, the higher the pressure will go. And that's what we play with during this process, is higher back pressure. So I work much better if I can see examples. So we'll work through an example to show you what this means. Here we have our original method on an HPLC system. We have a 15 centimeter column, 5 micron particle size. And this column therefore has the efficiency of 30,000, similar to what we saw previously in the table. Now, another thing to think about when you're moving your method to a smaller column is the chemistry of the column. So it's better to stay with the same vendor and the same brand, because every vendor will have a different bonding on their column, a slightly different selectivity, and therefore for a true method translation, you should try to always use the same brand when you scale the method down. So for example, here we have gone from the Avantor ACE 5 C18 PFP down to an Avantor ACE 1.7, so smaller particle size, but still the same chemistry, so C18 PFP. We've gone for a very short column, only 5 centimeters. And because of the dramatic change in column length, this is why we chose the 1.7 micron particle size. We've also got a smaller column ID of 3 millimeters. The length to particle size ratio is about the same. It's not exactly 30,000 plates on this 1.7 micron packing, but it's very similar. So the first thing we need is the column volume. That's the first thing we need to work out. And you can use this equation at the bottom of the screen to estimate the volume of your column. Or you can work out the column volume for your specific column experimentally. This is a very simple equation based on the volume of a cylinder, pi r squared h, but also including the porosity value, because of course our columns are not empty tubes, they have packing material in there. And so for a fully porous particle, 0.63 can be used as that column porosity estimation. And we've worked this out for the ACE columns, but of course you may see different values for different vendors. So we've chosen a shorter, smaller column, which has, of course, a smaller column volume, and the values are on the screen. What we need to do next is start to scale the method. And using that column volume we've determined and the original injection volume. So for this top method, we injected 5 microliters. What I need to do for my new method is times that by the ratio of column volumes, and it gives me 0.7 microliters. And that makes sense because I have a smaller volume column, I can inject less on that column. Now, you may be able to inject more, but for a true translation, you should scale the injection volume. And you will see in some literature, people have translated the method. They still have 5 microliters as their injection volume. And the peaks now look much more sharp, much larger, higher sensitivity. But actually, they've just injected more on column, which then shows as higher sensitivity. The risk with that is overloading the column. So for a true translation, you should scale injection volume down for a smaller column. We also need to scale the flow rate because I've changed the particle size and I've changed the column ID. So using the equation at the bottom, I times my original flow rate of 1 ml per minute with the ratio of column ID and the ratio of column particle size. So for this example, the equation is suggesting we go at a faster flow rate of 1.25 mils a minute. We can then use the final equations to work out our expected runtime and our expected back pressure. And you can see my original 35-minute run is now looking like a 4-minute runtime. So I've saved lots of time. But my back pressure, that was 66 bar, has now gone up to 559 bar. So I need to run this on a 600 bar system. What does that look like? Well, it looks just as good as the original method, but in 88% less time. So the resolution of the critical pairs remains above 3. The efficiency, looking at peak 6, is very similar, but I've saved 85% of my solvent and 88% of my time. So there is a very good reason for switching my method to a smaller column with a smaller particle size, because I can be very much more productive with the UHPLC column in this case compared with my original HPLC column. I just have to make sure that I scale flow rate and injection volume to make sure the selectivity remains the same. So the final method here is just as good as our original method. Of course, if you have a UHPLC method that's been provided by a partner or a sponsor, then you could use the same translation principles to go back to the HPLC method if you only have that instrument capability. And I think this slide really highlights the power of changing the column dimensions. Our original method at the top took 35 minutes for the peaks to elute. That means in 24 hours, I could run 41 samples. If I don't have a UHPLC system available, I can still speed this up. The example in the bottom right shows a 400 bar system, standard HPLC, but I've gone down to a 3 micron particle size and 100 centimeter length column, and I've over doubled the amount of samples I can run in 24 hours. So now, just by slightly smaller column, I can get 102 samples run in that 24-hour period. If I do have UHPLC available, a high pressure system, now I can go to the 5 centimeter column and run 360 samples in 24 hours. So that productivity will depend on your instrument capabilities. How many samples do you need to run overnight or over the weekend? Because that may decide which type of translation you prefer. So you can see for isocratic methods, it's quite a simple process. Choose the right column, scale the injection volume, scale the flow rate. Keep the chemistry the same. And those calculations, you don't have to do them all in your head. We made this calculator mostly to help us and our R&D team to translate methods. So this is an Excel spreadsheet. You can use it to translate methods. And the calculations, the algorithms I've shown you are already programmed into this translator. So you can complete the boxes, put in your column dimensions for your existing method, put in your chosen replacement column, and the system does the calculation for you. So it gives you the new flow rate, the new injection volume, and will tell you the runtime and back pressure. So I use this to check how fast we could go without exceeding the pressure limit of the system, for example. Now, there was a big update to the US pharmacopoeia back in 2014, and this suggested that you can change your method without having to revalidate your method if you keep the length to particle size ratio the same. And for isocratic methods, actually you can reduce the length to particle size ratio by 25% or increase by 50%. That means you have flexibility within those methods to actually modify your method and increase the speed of analysis, or perhaps get more efficiency, more plates, if you are struggling to get your method to pass. If you're running a gradient method, there's really not much flexibility, so you have to stick with the gradient conditions. But for isocratic methods, there's a lot of flexibility. And just showing you what that's like with a USP monograph for estradiol. I think the original monograph was based on a very old-fashioned column dimension, so 30 centimeters, 3.9 mil ID, 10 micron. And we thought we'd have a look at this method, see if we could speed it up within those USP guidelines. So we chose to go to a 15 centimetre column, 5 micron, which has the same efficiency. We scaled our method based on the same calculations I mentioned previously. So scale based on different column ID and different column volumes. And what that gave us very quickly was a much faster runtime. So from our original 8 minutes, now we've already speeded up the method to 4 minutes. This method passes our resolution requirements and is repeatable. So percentage RSD is below 2. That's keeping the same efficiency, the same length to particle size ratio. But we now have all this flexibility. We could go down in efficiency or up based on those USP recommendations. So any columns in these red boxes could be used for this method translation. They will look different. So, for example, if you use a column with a lower efficiency, so this is 25,000 instead of 30, now it's not quite as good as my original method, but I've got a 1.5 minute runtime. It's very fast. And if I have a lot of samples to get through, I like this method. If you look at the details, we've used the same scaling principles. If you need a bit more from your separation, here we've gone to a higher efficiency, 40,000 plates. And you can see still got a very fast runtime, only 2 minutes, and very efficient, very sharp peaks. The only thing to factor in when working on these translations is when you change the column ID, sometimes that has a negative effect on your chromatography. And we'll look at that later on. I mentioned these solid core particles. And you can translate from a fully porous column to a solid core column using the same principles. So here we have 5 micron C18 154.6. This is fully porous. If we want to move this to a solid core column, that's quite simple to do. We've chosen again a 5 micron C18 154.6. And you can immediately see for the later eluting peaks, I've got much better efficiency because they come off the column a lot more quickly. So I've not changed particle size or column dimension. I've just changed the format of the column. So I've gone from porous to solid core. Now, these solid core particles, they have less porosity and therefore less surface area. So we can't get as much C18 on the surface, which is why the runtime is so much shorter on a solid core phase. Now we can speed this up if we want to by choosing a smaller solid core dimension. You see here I should achieve resolution comparable with my fully porous. But for my early eluting peaks, I've lost the resolution. And this is what I mentioned with instrumentation. Instead of choosing a 4.6mm ID column, we chose a 3mm ID column. And the instrument we used was not optimized for these smaller column IDs. So there was too much extra volume, and that extra volume led to poor peak shape. You can see here, just moving to the 4.6mm ID column, I've solved that problem. I've got my resolution above 2. So do be wary that not all instruments are capable of running these smaller ID columns. And there's nothing wrong with choosing that 4.6mm, even when you have a shorter column. It will work on every instrument. So that was the simple part. The gradient translations are a little more complicated because we now need to factor in our gradient time and all parameters in the gradient. The first 3 calculations here are exactly the same as we had for Isocratic. We need to know the column volume. We need to translate our injection volume. We need to translate our flow rate. But here we also need to look at gradient time. So we have one extra calculation, and we need to think about the void volume in our instrument as well. So the dwell volume that remains on the system. Here we have a nice example of a 12 and a light mixture run over a 45-minute gradient on a 250 4.6mm ID 5 micron column. We've got critical resolution of 2.9 between peaks 9 and 10, and the peak capacity is 200. So that means how many peaks I can get in a separation window. The higher the number, the better, because that means they're sharper, narrower peaks. We want to speed this up. 45 minutes is a long time. So we're going to move to a smaller column dimension. Now, this large column has a lot of plates, 50,000 plates. To get comparable results, we're only going to a 15 centimeter column with a 3 micron particle size. That has the same efficiency, smaller volume. As before, we want to scale the injection volume. We're injecting less into a smaller column. And we want to scale the flow rate. So using the ratio of column ID and particle size, we get a faster flow rate. So here's the difference, this final gradient time calculation. And this takes into consideration our original gradient time, then the ratio of column volumes, and the ratio of flow rates. And we just worked out the flow rate. So this tells us our new gradient time is less than 16 minutes. And what it looks like is shown here. I've maintained my peak capacity. I've actually improved the resolution of that critical peak pair, and I've saved 40% of my solvent and 65% of my time. So it's very possible to speed up these gradient methods if they're not validated in your method and you don't want to revalidate. You can see again from this example how fast some of these separations can be. Here we've got a 15 centimetre down to a 10 centimetre column, which achieves triple the amount of samples in a 24-hour period. We also have the option to go to UHPLC with a gradient. And you can see here 250 samples in a 24-hour period. So 10 times what I was getting on my HPLC method. What you need to consider again are our column volumes. And when you have this solid core particle, which I've demonstrated on the screen, that porosity value is different. Potentially, you have 13% less volume when you use these solid core particles. So you can't run exactly the same method on a fully porous and a solid core without scaling that injection volume, the flow rate, and therefore the gradient time as well. So here we have an example with paracetamol and a porous to solid core translation gradient method. All of the calculations are the same. We're scaling each of those parameters based on our slightly smaller column volume in the solid core column. But we've actually kept the same dimension column. And you can see here, running the same dimension column, same particle size, I've got a faster runtime and a higher peak capacity. So there's a lot of benefits from moving your porous methods to solid core methods. Now, you could go even faster. Here we have a smaller column dimension and again reduced particle size to compensate for the shorter column. So now my 25-minute run only takes 6 minutes. If you're really in a hurry, then you can double that flow rate. That reduces gradient time by half. Now I've got my peaks all eluted with good resolution in 3.5 minutes. So it's a very powerful way to achieve fast separations. We need to think about the difference now with column volume and instrument dwell volume. And this is where sometimes methods should look the same on one instrument and another, but they don't. Especially if we follow a literature method and they don't state dwell volume on the instrument, and our system is very different, the peaks at the start of a gradient can look very different. So really, what we want is the dwell volume over column volume of our original method to be about the same as the dwell volume column volume ratio for our new method. If it's not, then you can get some differences in the chromatography. And I'll go into a bit more detail of this later. So, for example, this method, we had very big column, well, 15 centimetre column, going down to a very small column. The instrument was changed when we translated the method to one with a lower dwell volume. You can tell that from these equations at the bottom. But the ratios were not the same, which meant we needed to modify the start of the gradient so the methods look the same. If you don't do that, what happens is you get a very poor resolution of those early eluting peaks. And you can see this is a very fast gradient method. This is all done in under 2 minutes. And because everything is eluting so early, that is very critical. That instrument dwell volume is very critical. Luckily, our calculator works all this out for you. Takes some of the pain away. So you can type in your original column details, what you're translating them to, and your gradient method. So all the steps of your gradient, and this will give you the new steps for your smaller column dimensions. It also considers the instrument dwell volume to column volume ratio, because you tell the calculator what your dwell volume is. So finally, we're just looking briefly at transferring the same method between different instruments, which sounds like it should be very simple, but it can cause a lot of problems. If you have an isocratic method, it should be simple. You shouldn't see differences between instruments. But when you have a gradient method, this is when that system dwell volume really has a big impact. So it's easier to explain with an example. Here's your isocratic method. Looks very similar, independent of whose type of instrument you have, as long as you have, you know, good working practices for your instrumentation. When it comes to gradients, this dwell volume needs to be considered. So if you're not familiar with dwell volume, I would recommend you go back to the lab and work out the dwell volume for your instruments. What it is practically is the volume between where the solvents mix and the head of the column. So in a binary instrument where you have 2 pumps, the solvents mix at high pressure, and the dwell volume is the volume of this tubing through the auto sampler to the head of the column. If you have a quaternary system, now you have low pressure mixing, so it could be that you have a higher dwell volume, because now we have the volume from the proportioning valve through the mixer. It also includes the pump, the auto sampler, and this tubing to the head of the column. And these volumes, if they differ between instruments that you're using your method on, for a gradient method, it means that your compounds see a slightly different profile. Because practically, what this looks like is an isocratic hold prior to the gradient kicking in. And I've tried to demonstrate this here. The dwell volume is from the flushing of all that tubing. So you have isocratic hold before the gradient kicks in. And you can see here very different profiles depending on the tubing, the volumes of the mixer, etc. within an instrument. And they can differ dramatically between different vendors' instruments, or how you've set up your instrument. We did some work this week and we couldn't get the method to look like the sponsor's method. And it turns out we had 1 mil extra dwell volume on our instrument compared to their system. So we had 1 mil of extra isocratic hold at the start of our gradient. So earlier luting peaks didn't look the same. This calculation helps you to modify your gradient when you move to instruments. And very simple. You take the dwell volume of your first instrument minus that of your second instrument divided by the flow rate. That will give you an X number. This X will be either positive or negative. And if you have a negative result, it means you need to delay the injection. If it's positive, you need a pre-gradient isocratic hold. I think this explains it better. So what you want is your analytes to always see the same profile. If they see the same profile, you will get the same chromatography. In this first example, which gave you a negative result, I have my second instrument has a bigger dwell volume than my first, so I need to shorten that. And the way to do that is to pause before you inject your sample. And most modern software allows you to do this. If your second instrument has a smaller dwell volume, like this one, you get a positive result, and that means you need to add an isocratic hold at the start. So the analytes see exactly the same profile on every instrument. Working that through in this example, very fast gradient method for some vanillins, which we've run on our UHPLC instrument. You can see here it has a dwell volume of 0.574. We're just going to move that from a quat system to a binary system. They differ in dwell volume. So instead of 0.54 on my quat system, I only have 0.2 mils of volume on my binary. This gives me a positive result, which I can convert into a number for my minutes of pre-equilibration, pre-gradient hold. Showing you this as an example, run exactly the same method on both instruments, same column, same solvents, same everything. If I use the same gradient profile, I lose the selectivity of these last peaks, third from last peaks, and my resolution is now below baseline. It's only 1. If I add in that isocratic hold, so here I've added 0.29 minute hold. Now my chromatography looks exactly like it did on the first instrument, because I've added in that section to get the same gradient profile. So if you're seeing differences when you move your method between systems and it's a gradient method, consider the dwell volumes. If you can't change the method, then always build in some sort of isocratic hold at the start, because that will hopefully help to make the differences less critical when it comes to the peaks, because it often is these really early eluting peaks that it causes a problem with. So luckily, our calculator does this for you. It tells you in the transfer tab that if you have a different dwell volume, you may need to modify the gradient, and it tells you by how much to modify the gradient. So it's really useful. And you can use this with any vendor's instruments. So this is moving the same method onto different brands of instruments. So here, without correcting for dwell volume, we get a change in selectivity. But again, this has a different dwell. So we have a different pre-gradient hold, but we can achieve good chromatography if we use those transfer principles. Again, different systems, different dwell volumes makes it simple for you. And you can see here, hopefully, all the differences that can be achieved just by slightly modifying that gradient start. And I believe in the pharmacopoeia there is some wording to say that you can modify the start of the gradient based on the differences in instrumentation. So it probably is still a method change, but shouldn't have to be a full revalidation. So hopefully I've covered the method translations and transfers that I wanted to share with you today. Isocratic methods should be quite simple to translate, and you can save lots of time and potentially money on solvent and analyst and instrument time. Gradients are more complicated, but that calculator is really a very valuable tool to help you in transferring and translating methods. Finally, I wanted to show you some of the things we have to support you. Obviously, there's the translation calculator that's available free of charge. You can email me or Adrienne, and we can send you a copy of that. There are also these knowledge notes based on the actual science behind different parts of chromatography. So how to work out the porosity of your column, how to make sure your gradient is working properly, and also one on how to measure dwell volume. There is also a tab in the calculator in the translation tool to help you measure dwell volume on your instrument. I can't tell you what it is because it is dependent on the setup of your system. So you have to run a very simple scouting gradient to work out the dwell volume on your instrument. We always do that during our annual maintenance because it will change if you change the tubing or you get a new piece of your new auto sampler, for example. But this knowledge note can help you work that out alongside the calculator tool. So with that, I would like to thank you very much for your attention. Thank you again to Nova for asking me to speak, and have a great day. Are there any questions?
Bom, parabéns. Thank you, Emma, for your excellent presentation. Thank you for everyone for following us. And now I'd like to know if someone would like to make some asks for Emma about the presentation. Let me see. Gemma, they are asking about your email.
I have put it on this last slide. So hopefully you can see this.
Here. Ok.
Yes.
Aqui. O e-mail da Gemma está aqui no slide. gema.lo@avantorsciences.com. Essa é a primeira resposta. Estão perguntando se pode enviar uma cópia da apresentação. Sim, uma cópia da apresentação vai ficar gravada no YouTube, no canal da Analítica, que se chama Analítica Webinar. Então, você vai lá, acessa o YouTube. Quem está perguntando é a Jacilene Silva, de São José. Então, Jacilene, vai ficar lá no Analítica Webinar, que fica lá no canal do YouTube. A gente vai gravar essa apresentação lá assim que terminar, tá bom? Acessa lá. O que mais? Aqui, Gemma, a question for you. Can we change gradient flow rate and solvent proportion together? How changes that?
Okay. So I'm just going to go back to a slide quickly. Sorry. So when we translate our method, we always want to keep the same gradient slope. The reason we change the gradient flow rate when we change the gradient time is to maintain the same slope. If we change the proportions, then we're changing the slope. What that will lead to is a change in selectivity. So you can change it, but what will happen is your peaks may move around. You may get an improved resolution, but also it might cause a decrease in resolution. So you could get worse results if you change the slope. Today we were just talking about trying to get the same method. So you need to maintain the same percentage change in solvent as you do when you're changing the column. So you need to change the flow rate and gradient time together to keep the same slope. If you don't, that will start to change the proportions of the gradient. I hope that makes sense.
Ok, thank you. Então, Sérgio Bressan, foi respondido, Sérgio? Tá tudo ok? Ok. Vamos passar para a próxima pergunta. Gemma, Gilda Leitão is asking, how can detect if the lowering of resolution is a real volume problem?
That's a good question. I would say if you have the method working well on one instrument and then you move it to another one and you don't get the right resolution, that could be the dwell volume causing the problem. If you're following a method from a manufacturer, I would always ask them if they can provide you with the dwell volume. That could help if you can't reproduce their method. And again, if you're working with someone else who gave you the method, it's something really worth considering. Do both instruments have the same dwell volume? There's other things you could change to see if they're causing the poor resolution. If you have an old column, for example, perhaps that's causing the problem. But I think it's clear if you can put it on a different instrument with a lower dwell volume and see if it fixes the problem. That could be a good test.
Ok. Deixa eu ver aqui se tem mais alguma pergunta. Gemma, this is a question of Rodrigo Bessan. He questioned about outstanding examples on gradient methods.
I think that's a compliment.
Okay.
Yeah, he says happy. Yeah.
What else?
Or does he want more examples?
Mm-hmm.
We have other examples for step gradients as well. If this is obviously a linear gradient, but we also have examples for step gradients if people work with those. Anyone working with these curved gradients, they're very hard to translate. Yeah.
Okay, thank you. Let me see if there is some other questions. Gemma, is there advantages in using step gradients?
I would say it depends how complicated your mixture is. Most of these examples, I have 10 peaks maximum, and normally a linear gradient is fine for that number of peaks. If you have more complicated examples, or where you have very different polarity of your compounds, so you have some peaks very early, some very late, then a step could help to reduce the time of the method. So there are, I would say, advantages for more complex samples, but they are sometimes harder to translate depending on the instrument capabilities. So if you need your system to be working well and the proportioning to be right, really.
Okay, thank you. Is there another request for you? It is a question of Sérgio Cancho Gonzalez. Does a change the gradient affect much the resolution from 5 to 40% in 20 minutes to 5 minutes?
If you have the same, you need to keep the same slope. So if you run 5 to 40 in 20 minutes, you have quite a shallow slope unless you modify the flow rate. So you have this shallow slope in 20 minutes, but in 5 minutes, it's a much steeper slope. If you change the flow rate, you can get the slope the same and get the same results. If you change the slope of the gradient, you will see a change in resolution because it affects selectivity. Yeah. But you can compensate with the change in flow rate.
Ok. Mrs. Gilda Leitão request you about advantages in using step gradients. Now, she is requesting for steps gradients for plant extracts.
We've done some work with plants and agrochemicals. Some are very complex. We have a nice example with a very complex, many peaks. But with that sample, we just used longer columns to get the higher peak capacity. I can have a look and see if we have other examples or methods with the step gradients. We try to stick with the linear gradients where possible, but if there's areas in a chromatogram that are very bunched, so you have many peaks in a small part, adding a shallow gradient there can really help. So those sort of samples are the ones where I think the step gradients would be beneficial, because you're going to have a very complex mixture.
Thank you for your answer. Let me see. Yes, I think everything is done. Yes, no more questions. So I think you can finish. Yes. So thank you, Silva. Thank you for your presentation. Thank you for your time. Thank you for enjoying us in this morning. And I hope we have the opportunity to enjoy you in a next opportunity with another webinar. And congratulations for your excellent webinar. I hope to see you soon. Thank you.
Take care.
Ok, bye-bye.
Bye-bye.
Pessoal, muito obrigado. Nós estamos encerrando aqui nosso webinar. Eu espero que vocês tenham aproveitado esse webinar que a Analítica e a Vantor escolheram para vocês no dia de hoje, pensando em colaborar com a comunidade dos cromatografistas. E em uma próxima oportunidade, nós escolheremos um outro tema de agrado geral e voltaremos a convidá-los. Novamente, eu deixo, eu reitero, né, o aviso que esse webinar está sendo gravado e estará disponibilizado no nosso canal no YouTube, Analítica Webinar. Então, vocês podem baixar lá, vocês podem baixar essa apresentação lá e assistir eventualmente uma coisa que vocês gostariam de rever. E outras perguntas, eventuais perguntas, poderão ser feitas, né, através do e-mail da Analítica de Consumíveis, consumíveis@novaanalitica.com.br. E também essas últimas aplicações que a Gema mostrou para vocês, elas vão estar disponíveis para vocês, vão estar disponíveis no nosso site, www.analiticaweb.com.br, mas se vocês preferirem, vocês também podem nos solicitar, que a gente manda para vocês por e-mail, tá bom? Então, eu encerro aqui nosso webinar, agradeço a todos pela participação e espero vê-los novamente em breve. Muito obrigado, até uma próxima oportunidade. Bye, bye.